How do we retrieve data from qubits? Imagine trying to read a message that is both written and erased at the same time. That's what working with qubits feels like in quantum computing. The secret to getting data from them lies in a process called quantum measurement. Unlike classical bits that are either 0 or 1, qubits can exist in a superposition, meaning they are both 0 and 1 at the same time, described by complex probability amplitudes. When we measure a qubit, this superposition collapses, and the qubit becomes either 0 or 1, giving us a classical piece of data. The measurement process is inherently probabilistic. The chance of the qubit collapsing into 0 or 1 depends on its state before measurement. If the qubit superposition favors 0, then measuring it will most likely give 0, but there's always a small chance it could be 1. Once measured, the qubit no longer holds its superposition. It becomes a definite classical bit. This is different from classical computers, where bits are always in a clear state. Quantum algorithms play a big role in data retrieval. They prepare the qubits so that the desired information has a higher probability of being measured. For example, algorithms like Grover's search amplify the chances of measuring the correct data from a large set of possibilities. They do this by increasing the amplitude of the correct answer in the superposition, making it more likely to be observed when measured. Another exciting development is quantum random access memory, or QRAM. This technology aims to access data stored in superposition, meaning it can query many data points at once. QRAM could allow a quantum computer to retrieve multiple pieces of information simultaneously, speeding up processes that would take classical computers much longer. However, building QRAM is still a challenge because it requires very precise control and is sensitive to noise. Some advanced methods store information in the phase of a qubit rather than just its basic state. Think of phase as the orientation of a spinning coin. By manipulating this phase, quantum systems can perform certain calculations and data retrieval tasks more efficiently, often using fewer quantum gates. This approach can make the process faster and more scalable. In real quantum circuits, we use a sequence of quantum gates to manipulate the qubits into a state where measurement will give useful data. These gates prepare the qubits so that when we measure them, the results reflected the information we want. After measurement, the data is now in a form that classical computers can understand and use. Of course, there are challenges. Because measurement collapses the qubit state, we can only extract a limited amount of classical information at a time. Noise and errors in the hardware can also affect the accuracy of the measurement. To counter this, scientists use error correction techniques and repeat measurements to ensure they get reliable data. In summary, retrieving data from qubits involves carefully preparing the qubits with quantum algorithms, then measuring them to collapse their superposition into a classical bit. Technologies like QRAM aim to make this process faster by allowing simultaneous access to multiple data points. While there are hurdles like noise and hardware limits, ongoing research continues to improve how we extract useful information from these fascinating quantum bits.